we are looking for layout issues. Last time I did quickly show you some technology, maybe it is one better way to show you the exact process which makes IC possible. This is taken from Hart's handout from MIT lecture series, so you can go on web and check. Basic idea in all the making an integrated circuit or a device is to allow you selective area processing. That means in certain regions I want to do a processing, rest should get masked. So the word itself suggests something has to be masked. So the process which allows that particular area which you want to protect from the next process to go through can be created on a glass plate like a photo plate. Normally it is a photo emulsive plates. There are other methods, metallizations can also be tried, which is what hard masks are. But those masks have already pattern on as if like a negative of the photography film. So there will be dark areas and there will be clear areas. So this idea that the dark area can be opened or clear area can be opened decided by something what we call the resist type you use. Okay. So for example, here is a substrate and I have deposited a film in which I have to do some selective processing. So I say okay fine, I coat this with a photoresist, okay, something like this, and then I put a mask which has this area clear and the other areas dark. So if you look at the pattern, this is only cross section, but if you look at the pattern, it is something like this. This is dark area and this is clear areas. Clear means light can pass, no light can pass. So this is called dark field mask, the inverse can occur. This area may be clear and the windows may be dark, so it will be called clear field mask. So the mask is kept on this, of course it is right now kept as if it is kept distance, normally it is touching or very close to it using what we call proximity alignments. And when I shine light, light cannot pass through black areas, only it can pass through clear areas. And if say the kind of resist I have been using is called PPR, positive photoresist. So what does essentially it means that the positive or photoresist are generally materials of resins which have a long carbon cross-linking chains. Whenever the link actually fixes itself, it is a huge circular rings and then it is called unetchable, bonding is complete. Whenever chain breaks, then you say it is etchable. So the PPR, positive photoresist, has a property that it is initially hard, that means it is completely linked. Whenever light shines, photons actually received, the links break. So whenever link will break, that area will become soft, soft means etchable. The contrast to this could also be having a negative photoresist which says that initially it is open, that is it is a soft resist. Whenever light shines on it, it will become hard, that means cross linked and therefore unetchable. So the same mask with a different resist can do two jobs, is that clear? Or is that point clear? Just change the resist, or using the same resist, the complementary of this mask, wherever dark area there you make it clear. How do you make a complementary? Just take a contact print, okay. So you have a complementary mask, so dark will become clear, clear will become dark. So that same resist can be used for either areas to be opened or closed. So if I shine light, the resist which is below this clear area, let us say it was a PPR, becomes soft. So these area PPR becomes soft, the darker area PPR remains hard. Hard means normally etchable in most of the etchants which we use. If I do so, then I put that wafer on the inside a etchable, what is called the developer. Like a photography, we also develop here. So you push this into developer, the resist which is soft dissolves, resist which is hard does not dissolve. Is that clear? So since this part was soft, when I put into etchant, that part got dissolved, and since these were the dark areas where light did not go through, so that remained hard. So I removed resist from this area. Now if I want to create a window in this deposited film, which is the mask area which I have decided, then I start etching now that the film etching itself can start with the resist already on the top. Resist is a hard material, it does not get etched in the etchant for this film. So it protects this mask itself. So these areas resist of film does not attack. Only which is clear area, the etching starts for the film and you create a window down, and then the rest area is already protected. Is that clear? And then you remove, we call strip the resist. There are etchants which finally can remove the resist. They are normally organic materials, some other day, some other time. What are those? It depends on the film. If it is SiO2, hydrofluoric acid is etchant for this. If it is any other metal, like for example aluminum goes in orthophosphoric acid, so there are etchants and etchants, okay. Silicon etchants in HFHNO3 mixtures, so all chemical etchants, okay, all chemical etchants, okay. So remember those etchants do not attack resist and therefore etch, and normally it is believed, and which is what is shown here, that there is no lateral etching going on, but it will. In fact the way it is shown it will be lateral, but assume that lateral, this depth is not too much, so the lateral etching is smaller, but in that is called isotropic etching. Okay. We can do anisotropic etching where things go vertically down, but then we use gases which called plasma etchers, so the ions strike vertically down, okay. So they just etch straight way down. So I remove the resist and I have the window of the film. Now I can say I have films at different areas, the rest films I could remove. The converse could have been made if I would have just replaced this PPR by an NPR. These area would have been protected, the rest area would have gone out, okay. So this is a lithography process goes through. When I say I mask, I do this processing. Every time, let's say a CMOS process is 24 masks, 24 times wafers will see each time this some different mask and you keep etching some areas. Is that clear to you? So this is essentially the crux of all integral circuit manufacture. Now the problem started, the wavelength of the light which is used typically in photolithography, that is why it is called photolithography, is typical order of ultraviolet light which actually allows resist to expose. 2900 to 4200 angstroms is light wavelength which we use. However, this wavelength itself, if you see lambda is very large right now, 4000 angstrom is a sufficient wavelength. So if you are reducing your feature less than the wavelength itself, then the diffraction and refraction both starts and the pattern cannot be exactly etched out. So that lithography will not be correct. So you will have to reduce the wavelength of the light, okay. So from photo we may go to electron beams which can have then higher energy and lower wavelengths, then the photoresist will be different. There will be other organic material like polymethyl acrylate, many other materials can be tried. If you want further lower wavelengths, you can go to X-rays. If you want further this, you can go to ions. The larger the mass you pick up, the hit it will give to the material will be harsh and material will become actually non-crystalline. So one cannot use ion lithography very easily because it will actually damage the wafer itself. But no one wants to really do electron beam lithography because even electrons have high energy, therefore they are lower wavelength, so they will also actually damage the silicon below. So somehow what we do, we create the mask, this mask using electron beam lithography which is on a normally glass plate, okay, and use that corrected mask and use lithography like photolithography. But the problem there then is how good the patterns transfers. So there are different ways of doing it, and now what is the wavelength we are using is called extended UV below 193 nanometers, and there is a latest process which probably Intel will start working this year, EUV, okay, extended UVs. So these are the things which are going on. The other problem which technology people now getting because of 20 nanometer, 30 nanometers or less is they are such a small this, when I actually do whatever etching, the pattern which I see has nothing to do with pattern which was on the mask. So for example, I may have this actually, but what I may get is something like this actually. Now how do I get that area which I W bar I was looking for? Okay. So now the issues are, so do we what we do called phase masking, we do some DSP or image processing, we figure out for different patterns, if you are this pattern what do you really get, do an inverse transform and see if I want this what should be the actual pattern. Okay. But creation of that is not so trivial. Then there is called projection mask alignment. There are many techniques which are tried now for going to less than 20-30 nanometers. Lithography was very simple till 1 micron. As we went down, scaling, lithography people were first hurt. The major effort therefore went in lithography process. Okay. For electron beam can directly write on the wafer. You don't need any mask, you actually wherever resist you want you open, put light, electron beam can be very sharply focused through ACM. So I can actually write patterns on the wafer itself, but each chip will have so many transistors to write and there will be hundreds of chips on a wafer and hundreds of wafers to be done. This is called direct stepping. Direct write is very costly because every wafer has to go through hours of printing before you, that is very accurate but that is very expensive. So people who have money and who can sell the chip for $1 million can probably do that direct stepping. Otherwise photolithography at the end has to be performed for the larger numbers to be created in one go. Some image processing, new techniques, mass projection printing, many tricks are being tried, lower UVs are being tried, extended UVs as they call it, and this process is very hard. Right now no one knows exactly what is the wavelength Intel is going to use. The machines are made by themselves, the resist is of their own way and they are not right now allowing people to know what exactly this extended UV will be and can they go up to 7 angstroms or 7 nanometers. The problem which we see in real life is essentially called the mismatch problem. We have already seen in our analysis that if beta is delta beta plus minus, what can occur. Okay, we have seen all such variations can create what kind of actual problems for you. So now how to alleviate some of them, not that everything can be minimized, everything can be removed, but minimization can be tried. One technique is to get into a layout problem which probably can save some of your mismatch problems. So what first look at into mismatch? Factors causing transistor mismatch, as I said there may be number of ways because of this it can happen. One of course is, I yesterday said there will be many transistors on a chip, each mask will have different shifts and when you align they will have further different shifts. At the end of the day each chip will have different, everything different. So misalignment, then there is something called misalignment, when you fix one pattern over the other, whatever you say it is not 100% matched and as it goes sideways it goes further differently. So there are issues which is mismatch issues. Now first thing we must do how to model that mismatch. If you can model it partly we can take care in design. Then of course can we control it at the process and the device level, like threshold can be controlled to a great extent by different methods. So we try that. Then impact of transistor mismatch, one of the major worry in DRAM was or SRAM was the sense amplifier design and there the mismatch created a hell of this 1-0 was never guaranteed then and we are looking fast excesses. So there is first time people realize that this mismatch can create huge problem in the reliability of a DRAM. Of course one possible technique is to control at the circuit level. So you know how much is offset you have, you try to cancel as much as possible. If it is a systematic offset, what is systematic? Goes in one direction. So here is something which looks trivial. The way transistor works, you have a diffusion area, of course there is no color, 4 colors here, but maybe blue I call it red, black I will call it green, this is red and this is green. So normally what is done is first poly is printed, etched out and then implants have been done at the edge of poly. So this becomes N plus or P plus whichever transistor you are making and this also becomes N plus. But below there is a oxide, below all polys will be a thin oxide gate. Okay. So since this is the area where gate oxide below is available. So this is the channel length and this is the channel width. So fixing this diffusion area or source drain area and the poly widths decide the W by L of any transistor. So whenever I show you a green line intersecting red, there is a transistor below wherever is the common area. Okay. So it is called G intersection R. So here is that G intersection R shown. This is diffusion or N plus, and this is poly, which also will receive N plus when I am doing these implants. Now you tend to see 3 are almost identical as far as if you see the pattern, that say. But in real life the color shows that somewhere diffusion is larger, some is smaller, some is shifted left or small is shifted right. That is not visible so much from the pattern itself, okay. But in reality the process down has created the shifts, okay. Because as I say, lithography process is never guaranteed process, okay. Now these 3 structures after IC processing are not identical to each, and therefore these are so close by to each other and still they are not identical. If you are far away, unlikely that all will be of same value, okay. And how much you can tolerate is your design spec. This is called some other process, a halo, but let us call it. There is intrinsic factors which is causing the mismatch, which is called discrete dopant effect. Then there is the interface state fluctuations. Extrinsic, because of the process there is a random variation in gate length, gate widths, oxide thickness, implant dose, implant energy, anneal temperature, gate and source drain overlap, and spacer thickness. Spacer generally comes in the case of FinFETs, okay. So there are many variations going on, okay. These are called process variations. Designers must take care of process variation. These are statistical in nature. So some statistical analysis should be actually attempted. That is what we do sometimes. One of my PhD students work for this process, how to correlate process variation with circuit performance. Okay, as you reduce the channel, let us say the concentration because of the Vt which you are adjusting is such that the volume there, let us say 10 to the power 15 for sake of numbers, the channel length is less than 10 to the power minus 5 centimeters, 0.1 micron or lower. So what is the volume? 10 to the power minus 15. If it is lower, it will be 10 to the power minus 16, 17 per cc. So what is the number of carriers there? Less than 1, okay. So one cannot guaranteedly say where is the electron, where is the carrier, okay. So there is an issue which is called dopant effect, okay, random dopant effect. It will affect the off current, it will affect the on current, that is the saturation current, it will affect the thresholds, it will affect the threshold slopes, and it will affect the transconductance, and all are seeds and any other parasitics which are area dependent and dopant dependent will also get variations. So if you see a device parameters which worries you most at the circuits, because of the process variations all will be moving from one, and please remember our worry is on chip variation, chip to chip variation, wafer to wafer variation, and run to run variation. Run means 201 run, next 200 run. So we run to run variation. So huge problems. Okay. We do everything fantastic, we say everything is controlled, and then we see all variations. So if you look at the impact of process parameters on circuit, yeah, already I said current, capacitance, threshold, variation in threshold. So they may change speed, dynamic power, static power, and the worst is the yield. It will actually reduce the, what is yield? I decide this is the minimum specs I will expect, okay. Anything goes beyond that, that chip is not up to the mark, so that chip is wasted. So we say yield. So at the end, if you find your yield going below 50%, the whole process is of no use, okay. This statement is very interesting that there is, it seems as if there is a direct relationship, but there is a non-linear relationship because all the expressions are non-linear at the end of the day. So it is very difficult to actually predict which one will hurt you most and when, okay. And that is the analysis someone has to do, is called statistical analysis. Of course, as I say, some of them are correlatable, some are not uncorrelated processes, and then it's much difficult to actually predict things. Okay. I will not go into detail of statistics. This is an area of our students' PhD work. Just to give an idea, if threshold varies and there is a variance which is different for different processes, sigma of delta Vt. If you see this term, and I had taken an example of ADC. ADC is one of the major device in the analog to digital converters, which are most mixed signal, most important chip or circuit. So if you see, if I have a 7-bit ADC, the sigma allowed to me is around 5 to 6. Okay, anything below, let's say 5, yield is okay. But if you look at the 10-bit ADC, even a half a millivolt shift of sigma, the yield may go down, okay, 0. So the decision of making even this was done only for 0.25 micron process. If you do further down, God knows what will happen if 12-bit or 16-bit ADCs are used somewhere. So the precision and mismatch are very, very crucial in analog designs. As one example I am showing you, this is how the sample hold actually changes the equivalence of analog to digital. So 1001 pattern may become 10111 kind of thing, and which will not be representing the actual digital data for the analog. Okay. So there are issues which essentially process people know that at the end nothing will come, and therefore layouts become extremely, this is all just to tell you all that why layouts are so crucial at the end of the day, and layouts are the only thing which as a designer we create, the W by L, sizing, and then when you lay it out, things may work or may not work if you haven't taken enough precautions on that. Okay. As I said, basic layout design techniques should be taught by Professor Madhav Desai's course. That's the issue where digital designers should learn more about that. This course has no such area left in my course where we say layout design. Otherwise, layout editors is a part of any design process. Okay, so is that point clear why I am worried about mismatch so much? Because money, economics is worrying. 10-bit no yield, then what do? We made so many of them and there is none working well. So that is the issue which companies like National, TI, everyone is worried about, who sell ADC chips, okay, or analog. Is that okay? The issue is clear to you why mismatch is real worrying. So there are issues in layout. One is called orient, we will come one by one. Whatever is now following figures have been taken from Razavi. There is a chapter on this mismatch, word itself is mismatch there. So look for that chapter and I will show you what is the worry there. The issues of orientation of layout, symmetry, adding dummy layers, unit cell repetitions, and the last but not the least, the last but one is most important, called common centroids, and avoiding interconnect resistance. These are the issues which as a layout designers you must be. By the way, in design, when you design a chip, till you make before the metal mask comes, the process is called front end. That is, designers W by Ls have gone in, okay. So it's called front end. The rest of the process to make interconnects, back end, whatever, and this all issues related to this, these are called back end processes. These are torturous, boring, but they are paid higher than front end engineers, okay, because the testing is the last part which they come to it, and there is where they start looking things worse happening, okay. Okay, so here is something typical, this is shown to you. There are two devices shown here. One can see from here, this is the poly, that is, this is the gate which is shown here, okay. This is a P plus implant, this is an N plus implant, okay. And one can see, right now it's only one transistor shown, the other part I have not shown. This contact is essentially called metal 1. There are more than one metal possible, each metal is separated by oxide on the top. So what we did is, for this P plus implant for source drain we did here, what we now did, that opened a contact to the gate, to the source and to the drain. Okay, so this is essentially called active regions. And this and the any, so the method is, any metal 1 normally runs vertical, any metal 2 runs horizontal. Normally they are not running in the same direction or no angles. At layout should never be at 45 degree or 30 degree. Parallel coordinate, this normal XY system is always used. These lines are called Manhattan lines. Why? Okay, some of you might have visited USA. New York, Manhattan has avenues and streets. Exact Santa Cruz, if you go somewhere in Mumbai, avenues and streets. Okay, actually we copied from there. So Manhattan has all roads like this and all streets like this. So this is called Manhattan lines. Okay. So the way right now you can see, there are different directions I am taking metal out. Okay, and that is not acceptable to me. Okay, because if I do this process for n number of times, it will show you much more variations on this, unless I am symmetric to something. Okay, so I will show you what symmetry will show. So this kind of interconnects are not treated well, where you pick up connection anywhere, anytime and run anywhere, anytime. It is not a good way of putting your layouts. Okay. This is given in Razavi's book, specifically written, so you don't draw it, you can look into figure there. There another issue which is called antenna effect, and one can see this is a normal transistor. These are two devices shown here, for example, polys. Please remember, these are two transistors in series. Do you see them? Source, drain, source. So drain of the two are same, but it is only a matter of decision to say, because they are symmetric. This also we count source drain. So you say connect source and drain in between, or call drain or both together, whichever way you feel like, as long as the devices are symmetric. There are other devices called asymmetric. Those devices like LDDs and others, they do not have source same as drains, so don't connect like that. Now what we do is, though they look to be in series, essentially what does two transistors in series means equivalently of a one transistor? What does they show? Two transistors. Okay, before we go to there, maybe a simple figure can explain you. This is one possibility. Same connection. Second is this equivalent of what, and this equivalent of what? In this case the lengths are doubled, widths are same, or whatever you said. In this case widths are doubled and lengths are same. So transistor sizing, whichever you come, normally do not put huge size transistors. Break into either series or parallel combinations, so that the uniformity of each probably is much more maintainable. There is a word which we use in layout which is called aspect ratio. What is the word aspect ratio? Let us say this is the line, length. This is small, much smaller compared to this. So whenever I will do etching, I cannot guarantee etching here to here same, because I am going through a huge length. Okay, so the length here may not be same as length here. This is called aspect ratio issue. So don't run too long lengths, break into as many as you want, either using, if you want W to be higher or length to be higher, use either of the methods to actually break into smaller number of devices, large number of devices, to equivalently putting. For digital people, those who are doing digital codes, this also has an advantage. This is called gate stacking. सोचो क्या कर रहे हैं, ये बहुत ही important है लो पावर करने के लिए. सोचो फिर कभी. This is one of the most important technique of reducing power in a digital circuit. Okay. So now what we did, this is a similar transistor shown here. So one method was that, okay, you connect common gate together and put one big metal. There is a suggestion that if you have a single metal layer connecting to the contacts here and you run it longer as we did here, it gives like some kind of a resonator circuit on a oxide. In any insulator, if you run a metal line, it acts like an antenna, okay, it's a radiating system. This is what we do in MICs. Okay. Instead of there in alumina substrate or other substrate, you have silicon dioxide substrates. So it runs like an antenna, so it radiates power. So much of the, if you calculate the Poynting vector here, the huge power loss is at this end. Okay. So to divide this, we say, okay, the metal 1 where the contact is coming, which is the dissimilar discontinuity as we say, you make it that small and run another metal on the top through oxide through a window to that, which will actually take care of those contacts away from the actual this, so that the radiating patterns will be restricted only here, which has a smaller power loss. This is called antenna effect. Okay. So अभी आपको ये बता रहे हैं कि designers को क्या सोचना पड़ता है. Okay. If you learn like this, yeah, in some frequency it may still work, but higher the frequency you go, this will be one which will say the radiation is much more than the power delivered to you. Okay, so these are issues. Another issue which I just show random this connection. So one method is, for example, this is called surrounding. You can see here what did I do. There I have two gates. So here also I have two gates, fingers. These are called fingers, common point here. And the drain contact is taken in between. This is drain and this is source. Is that clear? Source on the outside and center is the drain. So I took drain here, source outside and connected them also. Okay. This is still a single transistor. Please remember, sources are common, drains are also connected. So what does it means? It's parallel transistors, two are connected here. Is that clear to you? This is essentially how it's called folding or finger structures. Okay. You can do larger numbers. If you have large number of WBIs to be connected, put equivalently this, sources on the top, drains on the up or opposite. All source drains are same, so whichever is source, whichever is drain, and in between run polys like this, zigzag. Okay. So you can make, can you now see these structures are more symmetric? You take symmetry across this or you take symmetry across this. Okay. So there is a symmetric structures can be created by actually folding them. Okay. Fold properly as much as you can and then see to it that symmetry is some way attained. Okay. This is called multi-finger transistors. Okay. The same statement which I made, if you have a very large size transistor wide, you can have two sets of them and in between connect. Okay. Multi-fingers and then connect together. Okay. So there are larger the size tricks to be, again you can see from here it is trying to get into more symmetric systems. Our ultimate aim is getting symmetric systems. Why I am looking for symmetry, anyone? Because whatever processing I will do, if all sides is similar, then they are likely to replicate everywhere the same. Aspect ratio issue will never come into picture. Okay. So larger the fingers I create, more likely I will get symmetric structures, and more symmetry means much more uniformity of etching if lithography is possible. Okay. Please don't draw because it takes hell of time and these figures are available just to explain you what is going on. Maybe I will put it on the web if you wish. The differential pair, which is the most common circuit you will use, you can see from here one method is you have one device here, you have another device here. Now you can see I have one poly, that is one input gate is like this, but the other is I made like this. Now it is not symmetric. The source I have made common. One drain is going but the other drain is away from each other like this. These lengths are different than this length for the contacts. Okay. So what should I do then? I should either do this or I should do this. Now you can see identical drains, identical source. So if you take symmetry across this, diffam has a symmetry, that is what we have been all the time saying, diffam has a symmetry requirements. So if you lay it out, only then that diffam symmetry is easily accessible to you. In this you can break more devices if you wish, but fold it, now this is called folded symmetry, do like this and again do the, but again it is symmetric. Symmetry is all that I am looking for any lithography process, okay, and therefore any layout I make has much more worry in symmetry points, okay. Is that okay? There is another worry which analog people gets problems into. Here is another problem which we observe is called, like when I was making that N-channel device, I have this oxide and gate delineated first and then implant, source drain. But it is the way implantation process goes, many of you might not be aware, those who are doing technology course in our other, they might have seen already implants. There is a columnar tube, maybe of any size of 8 inch or 12 inch, through which electron beams, ion beams of particular dopant or whatever implant you are doing is actually getting focused by electromagnetic fields, okay. When it comes as a focus beam, the wafer is orthogonal to it, okay. But the distance when the focusing is done by lens, electromagnetic lenses, the wafer does not have exact angle of 90 degree. You have to keep it at least 3 to 5 degree off some other day. It is a part of requirement for good implants. Now if I have an angle, this will get lesser, this will get higher because focusing here will not be there. This is going to happen, so I will tilt the beam anyway. 3 degree beam at least I will shift, maybe 5. So I will not actually have 90 degree orthogonal beams, okay. Further I will have to scan them. So when I scan them, it is like normally rasters are came, but some people do vector also. So when I flash back, there is a residual implant comes, okay. So when you come back to original position, there is a residual system. So on the left and the right, you do not get identical implants, okay. The reason is, you can now see this n plus and this n plus are, look you see here it is very internally very small, here internally it is larger. Larger the inside part essentially means capacitance is increasing, okay. This is called drain capacitance. What is the problem with drain capacitance increase? Your pole actually will move, okay. It may become dominant which wasn't there, okay. So what we do now in this, okay, this is 2 possible structures which are there. So we do something very interesting. You have these 2 transistors to make, you actually put another 2 transistors, okay. So now this transistor on its left sees another transistor, this transistor already sees another transistor, this also sees another transistor. If I take it away, this side is different from this side in between. So what I say is, to create a symmetry, I actually create dummy transistors on the left side or right side, okay. So it's called bias. So whatever bias I see on the one side, I see exactly identical on the other side. These are called dummy transistors. At least if not put transistors, at least put polylines, this poly to this poly, because there where the implant edge comes. So the minimum requirement in analog is every transistors, if they are not together, they must be surrounded by parallel polylines to create symmetry for implants. Is that correct? Yes. You can see from here, if I have a large beam coming, if I don't have this, there is a energy going other side. If I have back here, I have energy only equivalently on both sides, okay. So to keep energy distribution of the implant same on source drain side, I must have valves at both sides, okay. These are essentially valves for that, okay. Dummies as they, and they are not being connected anywhere, these are dummies. If you put transistor, you have area, put transistor itself. If you don't have area, at least put poly lines everywhere to protect your internal parts. Is that clear? So these if you see analog, this is what is needed. In digital, why we are not interested so much? Because noise margins are sufficiently high, any such things goes there, it will probably take care at the end of the day. There is no margin here, anything goes wrong, amplified. Okay. So that is very in analog. This word symmetry, you can see from here there are two transistors and I am connecting a metal something like this but no connection on this side. Okay. So do not do this. Okay. You do metal 1 and metal 2 and if you feel this is not needed, do not connect it anywhere. Is that clear? If M2s are not needed, do not run it anywhere, but near transistors, keep them. Okay. So any time you do on the left, useful, even if it is not required, put same thing on the right to have symmetry structures. Now I must tell you what is my worry with this. This is the next one which I will do as a circuit this, maybe you will get this figure. This is also one matching problem. If one is vertical poly, here is horizontal poly, never do the same, run always same direction. If you have this, all of them should be horizontal or all of them should be vertical. Of course, preferably do everywhere the same, but other cell you may do change also if you need connections the other side. So, but in the small area, whichever cell area you are creating, symmetry has to be 100% maintained. This is called orientation effect. There is something which Razali talks, but then I will give some maths behind. What we say from left to right, there is some variation called gradient of the sizing, for example. Okay. Because of the process whatever I do, actually there is a gradient in the process. Okay. Now what it can create, here is an example which I will show you. Assuming right now linear gradient. Linear gradient means it is much easier. In real life it may not be even linear gradient. Let us say the size of A pattern is twice, this is equal, so slightly equal to twice the size of B, and let us say there is a gradient on the left to right, linear gradient. So when actually I will print this, this will not remain double that of B, is that correct? This is essentially worrying us most, because then we decided two areas to be double, one double out of this, but in gradient this will not allow this to happen. So what we did is some interesting feature. Of course there are many other transistors should have, area should have been shown, but I just chose for one. Let us say the gradient is y is equal to mx plus c, linear gradient. Okay. For A1, let us say A is broken into two areas, A1 and A2. So I write A1 is mx1, this is for A1, mx1 plus b, b is the intercept, A2 is mx2 plus b, and b is mx3 for this plus b. Okay. Now if I write A1 plus A2 by b, I get mx1 plus x2 plus 2b by this. However, this does not become twice unless this becomes 2. Now this can only become 2 when the x3 is equal to x1 plus x2 by 2. Okay. Now this is an issue. Okay. This is an issue. x3 plus x1 plus x2 must be, average of that must be equal to x3. Now this problem which we see, if x3 is not x1 plus x2 by 2, a1 plus a2 by b2 is not equal to 2 either. Okay. So what we now do, we say okay, put x1 minus x2 and x2 minus x3 same, or essentially saying x2 should be x1 plus x3 by 2. If I do this, x1 plus x3 by 2 and put b here, okay, a1, a2 is across this, similarly a2 should come on the other side and a again. So this is called common centroid, okay, this is called common centroid. So if you have a circuit broken into a parts, I do not know where I have a figure, but I will show you what it shows. There may be blocks here along this axis, along this axis, along this axis, along this axis, it is identical. Okay. So let us say there is a variation from, this is A1B, for example, variation here, opposite will appear here. If I connect them, then variation in the two is getting cancelled. Is that clear? So I do always common centroid breaking into blocks so that the effectiveness of variation can be cancelled or at least minimized. So all analog designers should make their layout common centroid. So 4W/L का है तो दो के ऐसे रखो. So that, so in DFAM also you have two transistors, so M1, M2, M1/2, M2/2, M2/2, M1/2. Now you can see it is common to all four sides and therefore it will show minimum gradient effect. Okay. This is an issue which is called layout issue, which if you do not take care, then the problem will be the sizes of what you actually were creating are not getting transferred. Is that clear? So one difference from digital hardware to analog is every layout in analog is common centroid. Okay. That gives the maximum symmetry. At least if not that, do some symmetry at least. Preferably use common centroid, but at least symmetry you create minimum, that is what is expected. Now here is something very interesting data which is given by, not data, calculations given by Razavi. Same thing can be explained from here. You have four transistors, M1, M2, M3, M4. Let us say due to the gradient, it has the oxide capacitance of Cox. It is Cox plus delta Cox, Cox plus 2 delta Cox, this is Cox plus 3 delta Cox. So one possible technique is you connect these two and you connect these two. So what is the capacitance you are going to get? Ox 1 plus, there is no 3, so 2 Cox plus 3 Cox delta Cox, here 2 Cox plus 3 delta. You do this way, you connect this and you connect this and this, then Cox, 2 Cox plus 2 there, 2 Cox plus this. So essentially, of course this becomes 4. So depending on how much symmetry gradient you are expecting, you must decide which transistors should get gate connections, which transistors should not, which should be closer by. So do not put connection at least this. This is the worst connection. This is 2 Cox plus n, this is 5 delta Cox it will come. So either try this or try at least this so that you get symmetry as close as possible, which is created due to gradient in the process. Is that clear? So now all that I am trying to show you that why in analog layouts it is little different from, so Virtuoso, which is the famous layout editor in the case of Cadence, if you see analog designer, there is a separate shell in which you work. If you are a digital designer, you work in a different shell. The reason is this layout, both have Virtuoso, but they are different Virtuosos. Okay. So it is actually designed for analog, the other is designed only for digital hardware. Okay. So please use it, do not use Magic, because Magic is, it has no connection with anything, neither analog nor digital, it is only a graphic editor. Okay. So there you can do anything you like physically by forcing it. In real life, we are not allowed to force ourselves. System will actually tell you are going wrong, but you are always possible to overrule it. This is allowed. Okay, and but if you do that, you are taking a big risk on yourself. Okay, the circuit which I showed you earlier, I should have showed now. This is called common centroid. Is it clear? Half M1, half M2, half M1. You can even flip this. Okay, even better. सब जगह सिमेट्री बनाई है. So this is called common centroid. Okay. ये centroid है उसका. इसके चारों तरफ सिमिलर आना चाहिए, सिमेट्री आना चाहिए. ऐसा break करिए. Okay. The last part of this, we have only seen transistors so far. In analog, what else you need? Resistors and capacitors. Of course, we also need inductors, but this course we will not talk about them. Here the resistor, this you can draw, which is not a very big circuit. You can see from here, these RS and RD are not the transistor resistors I put, these are essentially the resistors which is source drain area resistors. Actually I should also put RG in case if you need. Okay. So how do I do this? If I have an N-well device, area there, I yesterday said you start with a P substrate and create a deep area which is called N-well. Well means 5 micron down or 3 micron down, that's why I call well. Please remember in circuit only first half a micron or even lower is the actual surface area you will use, surface depth you will use. All devices are within 5000 angstroms, okay. Then you don't need further. Then why do you need so much thickness of silicon? Because it's extremely fragile and to handle it at least you should have some stability. So for 12-inch wafer you can now understand why it should be very relatively much thicker, because 12-inch wafer will huge mass and it may just break jocularly by seeing, okay. So you must actually put some this so that it holds. So typically 1.5 millimeter to 2 millimeter thickness wafers are used for 12-inch. For 3-inch wafers 250 microns are sufficient thickness, but the device is going to be within less than a micron. But the wells are normally slightly below this, is that correct? Because device has to have substrate kind of effect for source and drain. So the wells are typically 2 to 3 microns, old time we used to make it 5 microns. So if in an N well, if I make N plus contacts, N well would have some resistive sheet resistance R rho by T. So RS is known, this is my length, there is a width in the inside this. So L by W into RS is the resistor value. So adjusting this and adjusting the second width of that, I can decide how much is the resistance I want. This, since it is a P substrate, this is a NP junction. So there is a depletion layer going on, is that clear? This depletion layer should not connect, okay. This is called punch through, the two resistors will get connected, okay. So there is a rule up to which two resistors could be brought together, okay. Normally resistors are created due to the implant areas available to you. So which are the areas available? Substrate, N plus implant, P plus implant, the on wells. So there are 4 RS available to you depending on the substrate at the highest lowest concentration, highest resistivity. So if you just take on a substrate to garnering, you create and put a contact there, you can create large resistors, okay, but normally not used. Whenever you need large resistors, which way you use? You actually create transistors in saturation region and your large amount of R can be created. The last part of this circuit is capacitances. You can see from here a capacitance, okay, I just told you last time, maybe before I go, there are number of, maybe we should use a fresh sheet. Let us say this is my first layer, I am making an N-channel device, I open a contact, there is a gate here, there is a poly here, these are all oxides, these are contacts. This is the first metal I took for source drain, and gate of course is in the vertically outside. So I put another oxide on the top, okay. Then if I want a contact with this, I open a window in this oxide and run the metal from the top, which then will get contact to the lower end. If I want a contact to this metal, I put another oxide on that and open a window here, open a window here where this next metal actually gets connected to the next metal. At no time this can directly be connected to the lower down, you must connect to the next nearest metal layer, okay. The catch is whenever you open a window here, there should not be another window below, okay, because the processes will then maybe intermerging somewhere. So if you open a contact here, open somewhere here, the next contact on the next layer, all contacts should never match each other, they should be at separated positions, okay, but you still go down and connect. Is that, these are called metal 1, metal 2, metal 3, metal 4, metal 5, metal 6, metal 7, and we are now going up to metal 9, okay. Why we need large numbers? Because many of the processors or DSP in particular, you need huge interconnect lines going from one place to the other. So our metal lines are similar, we can go as many metals. Of course there is an issue, why not beyond 9, why not 100? Oh, so the problem starts that the total resistance for the length of interconnect you go through will be so high that the voltage will drop there itself, nothing will go down, okay. So there is a length minimum you can, you have to restrict to. So in capacitors, normally between two metal layers there is an insulator. So there is a capacitor, wherever you make two contacts there will be a capacitance associated. But the way we actually do the capacitances in our this is the following. You have this process of transistor, but let us say in the top first poly line has been created for the gate, poly 1. Of course all poly will be protected below by oxides. Then, sorry, this poly I should use this. Then there is another oxide layer on this poly I created, and I put another poly here. This is called poly 2. It's called double poly process. Not all processes are double poly. All flash processes, flash ROMs are, they all are double polys. But not all CMOS processes are double poly, but analog CMOS processes are always double poly. So extra money for that. Okay. So this is poly, oxide, poly. So that is the most common capacitor used in analog designs, created in analogs. If you don't have one, there is another way of doing the same thing which I was showing you. Instead of calling this poly, this is called metal 1. And this is metal 2 or 3 or 4. So restrict the area of metal. So you have a capacitor down which is called MIM capacitors, which are called MIM capacitors. Please remember, once I use this line, I must break it somewhere because otherwise there will be one line everywhere. So the area for each has to be restricted to make a standard area of capacitance. Is that clear? So restrictive area will make standard epsilon A by D kind of thing. So either MIM capacitors are used, or poly, if you have two poly process, poly 2 to poly 1 is what is used often in our processes. Most people have poly 2, if they don't have then you use only MIM. Digital process will have MIM because there are 7 layers available or 9 layers available. Now there also it is decided the capacitor should be closest to the point where the node capacitance is to be created. Otherwise for us parasitic capacitance will actually shift our poles, okay, or zeros. So in analog the position of capacitance to choose has to be which node you are actually looking at. So closest to that you actually bring your capacitances. Instead of having a large capacitors, you can actually create small capacitors of C1, C2 or C1 and then connect in a fashion. But do you see this capacitance is not connected to anywhere? These are connected 6, 6, 2. So 8 capacitances are connected to give 8, let us say this has a capacitance of 1 or C, this is 8C. Is that clear? This is C and this all are in parallel made, so there are 8C. Where do you think such things are needed? In a switch cap circuits, you actually will use 2 such capacitances. This will be 8 times this, okay. So if you want to do this circuit, use this kind. You make a round, Now all that I have not shown and even Razari has not shown, you need dummy everywhere. All areas must be put dummies all around. So 8 of them and further 8 of them around just to keep them identical to each other. Is that clear to you? So this is something not shown, but please remember every this has side should have equivalent dummies, top, bottom, side, everywhere. So this is net, but then you should have here, here, at least poly as I say, here, here, everywhere. Okay. This is essentially, it's called 8 to 1 capacitance ratio. This circuit is creating 8 to 1 capacitance ratio, 8 from this, 1 from here. Okay. Change this combination and you can create any other ratio as well. The last slide for the day as well as for this layout part is this interconnect routing. Now this is an issue which is available, it is equally troublesome in digital but shown only for analog here. Let us say you have a current mirror which is mirroring so many of them. Like you have M6, M6, M5, M, so much even in op amps. Okay. Now whatever way I use this line which is called the ground line, okay, or VSS line, one can see from here between here to here there has to be some metal line running and it does not have zero resistivity, okay, it has a finite resistivity. So equivalently saying from here to here there is a resistor, from here to here there is a resistor, and if this is taken little longer, so this potential will be different from this potential when the current is sinking through. Is that correct? These are sinks. So when all of them are sinking because of the mirrors, this sink will be different from this sink. Is that correct? Because the available current to you is now the voltage drop is actually created across. Okay. This is called ground based resistance problem. In the case of digital, even if there is no mirror, because of this we receive what we call ground bounce. The actual zero shifts to a higher potential. So your noise margin on zero become worse, sometimes even not there. Okay. So it's called ground bounce. Similarly, it comes from the power supply side, it's called power droop. So it comes down and your upper noise margin also can go. Okay. So these are issues which layout people. So what should I do for R to be minimized? Increase the area. So thickness of this metal, analog grounds are therefore at least 8 times that of digital grounds, thickness wise, at least 8 times. So if you see an analog ground, huge plates kind of grounds are provided so that the R's are as small as possible. Is that clear? That is the trick. But what is the penalty? Area you lose, but at least survive, otherwise you don't survive. Okay, so that's the issue in the case of layouts. Okay. Also, now I will say you don't use single references. Okay. Even if it doesn't matter if you run through as far as circuit things, but run another circuit ahead, another mirror and run ahead. Okay. So break into number of references in case you feel too many such things you are running from one point. So don't run from one point. This is also done in digital, keep buffering or actually putting VDD lines on 4 places. If you see a normal chip, there will be at least 4 VDD contact and 4 VSS contact. Okay. Though you need only 1 VDD and 1 VSS, but the distance from each of them may be different. So at least 4 corners you create 4 VDDs, same way 4 VSS. Okay. This is done even in, so jitna you think you can tolerate, keep as many and then repeat again. Okay. That is extra area but saving your life further. Okay. So these, are you now clear to you that why I spend time in analog layout is the issue is that things can fail at the end just because you were not aware or you were lax in layouts. Okay. Things will finally yield may show you 0. Okay. So all analog designers must spend their 50% time after so called the simulation results have come in actually getting the best layout. Okay. Try any number of times, extract it and put it every worst values for them and see where it still works for you. Okay. Increase the ICMRs, decrease the ICMRs, swing rate, power supply 5% to 10%, where you keep seeing that everywhere circuit is all bounds, it actually works. Increase temperature from minus 25 degrees centigrade to 125 degrees centigrade, run whether all corners it works. Then keep modifying your layouts till you find most of the corners are met. So that requires hell of an effort, okay. Most of our students copy from the last year thesis because he must have seen some, and no one has seen in the first. So the worst things are going on last 10 years, okay. Okay, so this finishes much of the issues on layout. There are many more things I can tell, but forget this. We'll start with next Wednesday the last topic of this, which is called oscillators. We have done a lot of amplifiers, at least see oscillators. Actually oscillators are not just the VCOs which we are interested in. We must do something called PLLs, phase loop locks. But I think in next 3 hours, 4 hours, I don't think I will be able to catch up with PLLs, but I will at least tell you how PLL works on Friday. So on Wednesday, I may show you VCOs. On Friday, I may show you how PLL picks up, why PLLs are essential with VCOs.